Welcome to Advanced Linear Algebra. Today, we are going to explore a profoundly powerful concept called diagonalizability. If you have ever felt overwhelmed by complex, messy matrices that seem to mix every single coordinate together, you are in the exact right place. In this lecture, we will learn step by step how to completely untangle them. Now that we know our goal, let us understand the problem. Imagine a massive, tangled ball of cables behind your television. Pulling one cable accidentally pulls three others, making it impossible to fix anything easily. A standard mathematical matrix behaves exactly like this, mixing all coordinates together in a messy, interconnected way. Diagonalizability is the mathematical process of completely untangling those cables. When we transform a matrix into a diagonal matrix, all the off-diagonal numbers become zero. This means the matrix only stretches or shrinks each direction independently, without mixing them up at all. We achieve this clean state using a similarity transformation, which simply changes our perspective. To actually untangle this matrix, we need to identify special properties called eigenvectors and eigenvalues. Think of an eigenvector as a special direction in space that stays perfectly straight. When the matrix is applied, this vector is not knocked off its path or rotated. The eigenvalue is simply the numerical stretch factor. It tells us exactly how much that specific eigenvector is lengthened, shrunk, or flipped. If we can find enough of these independent straight directions, we can build a brand new coordinate system where the matrix behaves perfectly straight. This is the core secret to breaking down complex transformations. This brings us to the fundamental relationship that defines these special directions. The equation is AV equals lambda V. Conceptually, this means applying the complicated matrix transformation to our special vector produces the exact same result as simply multiplying that vector by a single number. A is our original messy matrix. The vector V is our eigenvector, the direction that stays straight. And the Greek letter lambda is our eigenvalue, the scaling factor. If lambda increases, the vector stretches further. If lambda is negative, the vector flips in the opposite direction. This simple equation is the foundation of everything. Now that we understand a single eigenvector, let us upgrade this concept to handle all of them simultaneously. If our matrix is size n by n, we need exactly n independent eigenvectors. We pack these vectors side by side to form the columns of a brand new matrix, which we call P. We then place all the corresponding eigenvalues down the center of a blank matrix to create a diagonal matrix called D. Grouping everything gives us the equation AP equals PD. This states that applying our original matrix to all special directions at once is mathematically identical to scaling them by the diagonal matrix. Our ultimate goal is to isolate the original matrix A to see exactly how it is built from simpler parts. By multiplying both sides of our previous equation by the inverse of P, we get the most important formula for diagonalizability. A equals PDP inverse. This formula tells us that any complicated matrix can be broken down into three simple steps. First, P inverse changes our perspective. Then D stretches the space easily. Finally, P changes the perspective back. If a matrix can be written in this exact form, it is officially diagonalizable. Before we calculate anything, how do we know if we will have enough eigenvectors to build that matrix P? We look at two concepts, algebraic and geometric multiplicity. Algebraic multiplicity is how many times a specific eigenvalue appears as a solution in our math equations. Think of it as a blueprint, saying a house should have 3 bedrooms. Geometric multiplicity is the actual number of physical independent eigenvectors we can find. For a matrix to be diagonalizable, the built reality must perfectly match the blueprint. The geometric multiplicity must exactly equal the algebraic multiplicity for every single eigenvalue. Let us see this with a concrete example. We are given a 2 by 2 matrix A and we want to find the matrices P and D that break it apart. First, we must find the eigenvalues by solving the characteristic equation, setting the determinant of A minus lambda I to 0. We subtract lambda from the main diagonal, multiply the diagonals, and subtract the off diagonals. This gives us a classic quadratic equation. Factoring it reveals our two eigenvalues, 2 and 3. This means the matrix stretches space by a factor of 2 in one direction and 3 in another. Now that we have our stretch factors, we need to find the specific directions or eigenvectors for each one. We plug our first eigenvalue, 2, back into the matrix equation A minus 2i times v1 equals 0. Solving this system reveals that the first eigenvector has coordinates of 1 and 1. Next, we repeat the exact same process for our second eigenvalue, which is 3. Subtracting 3 from the main diagonal and solving gives us our second eigenvector with coordinates of 2 and 1. We now have both of our special independent directions ready to use. With our eigenvectors and eigenvalues found, we can construct our final matrices. We build the matrix P by placing our two eigenvectors side by side as columns. This represents our new untangled coordinate system. Then we construct the diagonal matrix D by placing our two eigenvalues down the center diagonal, making sure they match the exact order of the eigenvectors in P. We have successfully found the pieces needed to diagonalize the matrix. Physically, this means we have proven that this specific matrix can be perfectly untangled into independent straight lines. Before we look at a matrix that fails, let us visually summarize the successful untangling we just calculated. On the left, you see the messy, skewed grid created by our original matrix A. Notice how moving along one axis forces you to move along the other. On the right, we have switched our viewpoint to align with the eigenvector arrows we found, v1 and v2. Suddenly, the grid becomes perfectly square and independent. This visual transformation is exactly what the formula A equals PDP inverse achieves mathematically. Now that we have seen a successful visual transformation, it is crucial to understand that not every matrix can be untangled. Let us look at a matrix B that represents a shear transformation. Because B is an upper triangular matrix where all numbers below the diagonal are 0, its eigenvalues are simply the numbers sitting on the main diagonal. The only eigenvalue is the number 1. Because it appears twice, it has an algebraic multiplicity of 2. The math blueprint tells us to expect 2 independent eigenvectors. We must now test if reality matches this blueprint. To find the eigenvectors, we subtract our eigenvalue, 1, from the main diagonal of matrix B and set the result multiplied by vector x equal to 0. This leaves us with a matrix that is almost entirely zeros, except for a single one in the top right corner. Multiplying this out gives us the equation that the vertical coordinate x2 must equal 0. The horizontal coordinate x1 can be absolutely any number. Because x2 is strictly trapped at 0, all possible eigenvectors must lie perfectly flat on the horizontal axis. Because all eigenvectors lie on that single horizontal line, we only have one independent direction. This means our geometric multiplicity is only 1. Remember our blueprint? The algebraic multiplicity was 2, but the geometric multiplicity is only 1. Because reality is less than the blueprint, we do not have enough columns to build the matrix P. This proves that matrix B is completely impossible to diagonalize. Physically, this means the shear transformation permanently tangles the coordinates, and no change of perspective will ever untangle them. Now that we have seen how this works, why do we go through all this effort? Understanding diagonalizability is absolutely critical for solving complex real-world problems, especially when we need to multiply a matrix by itself many times. If you want to predict a city population 100 years from now, doing it with a standard matrix requires millions of tedious calculations. But if the matrix is diagonalizable, you simply raise the numbers in the diagonal matrix to the power of 100, which takes a fraction of a second. This massive shortcut powers Google search algorithms and quantum mechanics. Let us summarize what we have learned. Diagonalizability is the ultimate tool for simplifying complex linear transformations. By finding a matrix's eigenvectors and eigenvalues, we can untangle its interconnected coordinates into completely independent paths. We learned that a matrix is diagonalizable only if its geometric multiplicity perfectly matches its algebraic multiplicity. While not every matrix can be diagonalized, those that can allow us to bypass massive computational hurdles, transforming difficult problems into simple, isolated calculations. You have now mastered the core mechanics of diagonalizability.